So very good afternoon to everyone. So I am Rohit Gehlot and I will be taking the week 7's materials characterization problem solving session. So in the week 7 majorly the uh, things which were taught were the about the X-rays, their source, generation and all. So I will be so as already like in the yesterday's week session, like a lot of problems are already been discussed. So majorly I will be covering the theory part and in the subsequent lectures coming the next week we will be discussing more and we'll go deeper in the problems also, and also we'll be discussing some real life experiences and real life problem solving sessions on the x-rays. So if we talk about the x-rays, like the first question is like how to probe structure of the materials. So any kind of structure, like any kind of crystallographic information like or lattice parameters or atomic positions, how we can determine for a particular material. So we can say like x-rays are the agent for this. Like with the help of x-rays we can determine the crystallographic information like lattice parameters and atomic positions and many and much more and many more other details. So x-rays are very important nowadays. XRD is very important tool for this. So in this diagram, as it can be seen, there is an X-ray tube, which is a source of the X-ray generation. And from this, the X-rays are falling on a sample. This sample can be a metallic sample or a powder sample or some polymeric sample also. And then the response of this is detected by a particular detector. And then this is shown in your like output or in your computer. So where you can see, if we see like this is the diagram of the simple XRD with a protective shielding emitter. So this is your X-ray tube and your shield, and this is your sample holder, and here is the divergence slit, and this is your counter and pre-amplifier, and then the detector, and here we place the sample. So for the first thing is that your why X-rays are so much popular now these days, and what are the basic properties of the X-rays. So if we see that X-rays are much more penetrating than the light because they have higher energy, and also like they easily pass through the human body. That is what you can see here. That is why the X-rays are very much used in the radiography also. So by placing a source of X-ray on like for this type of image, like we place source of the X-ray on one side of the object and photographic film on the other radiograph. So by this way we can see like the details of if any human fracture and some kind of tensile stress defects and all. So the major thing is that the less denser of portion of your object allow a greater portion of your X-rays to pass through than the more denser. So that's why we can see the X-rays were first detected by the or discovered by the Röntgen in 1895. He got a Nobel Prize in the physics at on 1901 for this. X-rays have so X-rays are like the electromagnetic radiations of exactly the same nature as light, but it has much comparatively shorter wavelength, and the wavelength of the X-ray is in the range of around zero point 0.5 to 2.5 angstrom. But for the visible, it was around 6,000 angstrom. Okay, though so the two first two so the three things that are important. The first one is that these are the electromagnetic radiations, and these affect the photographic films, and their wavelength is much lesser than the visible light, and X-rays penetrate more compared to your visible light. Therefore, they are used for detecting uh, bone failure and other details. So, so this is so how the X-rays are produced. So, firstly, the first this is the schematic cross section of an X-ray tube. So here, like it comprises beryllium window, tungsten filament, and glass. So this is your tungsten filament. So firstly, the current is passed through the filament or your cathode. Generally, it is used tungsten. So due to this current, due to the current passing, the heating of your filament happens. And when this overcomes the work function of the material, then the loosely bound electrons or the outermost cell electrons starts to emit, and as you can see, like these electrons are emitting, and then they maintain a potential difference once between the cathode and the anode of around 10 to 30 kilovolts. So there is a, like when the potential difference between your cathode and the anode is around 10 to 30 kV, then these electrons start to draw out from the cathode towards the anode, and then further these electrons will hit your target. This is your target, and then start to deaccelerate. And why they start to deaccelerate and what happens in that, like we will be discussing in the later section. So after that, these start to emit your electromagnetic waves, okay, and due to which the X-rays are generated. So we maintain a proper vacuum system in the X-ray tube, and a beryllium window at the top allows the X-rays to come out of the tube. So this is the beryllium window. From here and here, your X-rays starts to come out of the and then it's like sequentially collimated and to fall on your sample. So I hope this is clear. So once your X-rays are generated, the rays coming out from your target, like it consists of a mixture of different wavelength and with varying intensity, and further the uh, this lambda is highly dependent on your tube voltage, you know this. So the tube voltage on which for which the tungsten filament was working on, your intensity is so from this, like you get the plot like this. So 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 as written here, as I have written here, X-rays of multiple wavelength come out of your beryllium window, and then there is a term known as lambda SWL, which is a short wavelength limit. So we can define it as uh, I can say, so the electrons which are like stopped in your one impact, as the electrons fall on your target, and which are completely like a series of things can happen, like some lose their energy partially, some lose their energy completely, and the electrons which lost their energy completely and stopped in the impact will give rise to the photons of the maximum energy, or photons of the maximum energy, which means like the rays of minimum wavelength. So these are the points where the rays of the minimum wavelength are present. So at that, when you're so at this point, your minimum wavelength is defined as your, we can write it as c by nu lambda, c by nu, and then we can write it as in terms of Planck's constant, and then hc by e nu, where what I have written here, nu is equal to, and then your intensity. Okay, so there are three things, like three curves, A, B, and C. Okay, so these are the electrons coming to rest at a plural scattering, or so as seen here, like A, B, and C. So the electrons coming to the rest after multiple scattering, okay, or deacceleration. Then your this is the lambda SWL. So after single impact, here what I have written, like here, after single impact, one, if the electrons coming to completely rest, then it can be written, this condition can be defined as E nu is equal to H nu. EV is the energy of your electrons, and then when it completely comes, then it converts to photons of the maximum energy. So I written at H nu. So here, from here we can define your lambda SWL as this. And one more thing is that your current at these L lambda SWL, your current is 0 up to a certain wavelength also. At at those current uh, at those lambda where current is 0, it's called your SWL, and then it increases rapidly to maximum and decreases afterwards with no sharp limit on your long wavelength side. Okay. Now one more thing comes here, that what are the parameters on which your lambda SWL depends. Okay, so we can say that as your tube voltage increases, your intensity of the wavelength increases, and both SWL, that is your lambda SW, and position of the maximum shift, yeah, like the position of your maximum shift to your to shorter wavelength. So therefore, as your applied voltage will increase, the number of photons per second emitted will increase, and your average energy per photon will increase. Okay, so keep this point in mind. And the total energy or total X-ray energy emitted per second is your proportional to the area under, like, these curves, area under one of these curves. The area under one of these curves will define the total X-ray energy emitted per second. Okay, and another parameter will be the atomic number on which the target, on the target which is it is falling, and the third one is your tube current. So therefore this depends upon your these parameters. A, this is a constant, then Z is your atomic number, and then your voltage, and A and to the power m, this is the constant. Generally it is 2, around 2 or 2 or around 2. So like if we move to this, so continuous spectrum is caused by your rapid deceleration of electrons by the target, and then the origin of your characteristic spectrum lies in the atoms of the target material itself. Okay, so this is the characteristic, these are the characteristics X-rays. Okay, so these are your characteristics X-ray. So in the characteristic X-ray, like as I told us, that these are the continuous spectrum is caused by a rapid deceleration of the electron, right? So if one of the electrons bombarding your target, like if it has sufficient kinetic energy, like it can knock an electron out of the K cell, right? And then due to this leaving of the atoms in a higher energy state, like one of your outer electrons immediately falls into the vacancy of the K cell that was created by due to the impact, and due to this the characteristic X-rays are present, are formed. So there are majorly three things are considered: K alpha 1, K alpha 2, and your K beta. Okay, so this is how your origin of your characteristic spectrum takes place. So the incoming electrons is knocking off an K cell electrons. Okay, so this is the incident beam. Due to this, the K cell electrons were emitted, and then the L cell electrons moves to your K cell vacancy. Then due to this, the K alpha 1 generates. So if here it is written that if it moves from L cell to K cell, then K alpha 1 will be generated. If it moves from M cell to K cell, then K beta will be generated. And if it moves from K cell to L cell, then L alpha will be generated. So here I've written that K alpha 1, K beta, and then L to K, smaller quantum jump, right? From L to K there is a smaller quantum jump. However, from M to K there is a larger quantum jump. Okay, so there will be, therefore the K alpha 1 will be have a higher intensity compared to K beta. Okay, but however the K beta has higher energy than K alpha 1. Okay, sorry, so yeah, K beta has a higher energy than K alpha. So uh, the thing is that your one second. So if till now, if anyone has any doubt, we can discuss. Okay, so now comes the Moseley law. So the Moseley law equation is given by this: root of V is equal to C multiplying by Z minus alpha. So the wavelength of any particular line it decreases as the atomic number of your emitter is increased from this relation. So this is the relation between mu. So from here also it can be seen that so as your atomic number is increasing, the wavelength of your any particular line like k alpha 1 or L alpha 1 is decreasing, okay, as your atomic number is increasing, okay. Okay, so this is your wavelength. So it is like that as you move from left to right, it is decreasing. However, your atomic number is increasing as you move up. Okay, so the wavelength of your any particular line, like whether it is k alpha 1, L alpha 1, or k alpha 2, will reduce as the atomic number of your emitter is increased. There is a linear relation between the square root of your line frequency mu and the atomic number z. For copper, your lambda is around 1.5406. This is generally used in your X-rays. Okay. So now, if we see the interaction of your X-ray with your matter, with the target, then generally the absorption is the major phenomena. So as you can see, like this is your target material of particular thickness X. So as the X-rays falls of your intensity I0, and then it comes out of as IX intensity. So some of the intensity is it has absorbed. Okay. So 1 second now. Okay, so this is the your fundamental of your absorption, this light source. So this is your incident photon, okay, and these are your particular KLM cells, okay. And then as like it is striking the incident photon, so this is your photoelectrons, okay. Then your auger electrons are these, like due to this the energy difference, if some electrons removed, then your auger electrons uh, are generated. While if the X-ray is that this is striking your K cell, if your K cell electron is removed, and then your upper some lower energy like cells go to this, electrons move from this to this, then your X-rays are generated. Okay, so role of the nickel filter. So generally for your analysis we want to have separation of your K alpha and K beta. So generally nickel filter is utilized, so it bypasses the K beta. So we are able to get K alpha, but still it is a problem like K alpha 1 and K alpha 2 separation. So continuous and characteristics X-ray. So for the characteristics X-ray, it can be written as a function of your Bi V minus Vk to the power m. B and m are constants, and V is your potential difference between your filament and the target material. Okay, and this K is your excitation voltage, and then this I is your tube current. However, for the continuous spectrum, it is given by A, I, Z, V to the power m, where A and M are constants. And V is your potential difference between filament and the target material. I is your tube current, and Z is your atomic number of the target. Okay, so the two the relation between your continuous and the characteristic X-ray is given by these two equations. Okay, so the characteristic X-ray depends on your tube current, potential difference between your filament and the target material, and your excitation voltage. Okay, however the continuous spectrum depends on your tube current, which is same as the characteristics, atomic number of the target, which was not in your characteristics X-ray. Okay, So here, like, this is like 10 kV ratio, 20, ratio 25, ratio 30. So as it is increasing, then your K alpha and K beta are generating. Okay, so K beta can be removed by your nickel filter. And then uh, your characteristic X-ray, this one. Okay, these are your continuous spectrum. The continuous spectrum depends on your tube current, voltage, and your atomic number. Potential difference between your filament, and this depends on an additional excitation voltage, KL, excitation voltage of that particular material. Okay, so this is how the interaction or your absorption is like determined. So we can, the rate of change of your current is a function of your linear absorption coefficient of the particular material. It depends on your material to material, it may vary. So therefore we can derive the current in terms of your linear absorption coefficient as Ix is your I0 the e to the power minus nu x, and then your Ix is I0 e to the power minus, if we write it in mass absorption coefficient, then nu by rho to the, then x we can also write in terms of rho, then it is rho time dx. Okay, so for steel it is around 7.8, and for magnesium it is around 1.8 gram per cc. Then we can write nu by rho average can be written as a summation of w1 nu by rho 1 plus w. If your material is non-homogeneous, then your nu by rho will be like this, by can be written by this. So now there are like soft x-rays and hard x-rays. Okay, so nu by rho is your function of your lambda cube to the, and the atomic number. Okay, so these, the more details can be like elements of x-ray diffraction by BD Khalid. In that book more details are given. Then if we further move to the fundamentals of absorption and the scattering of the x-ray by atoms. So like suppose for the lambda is around 2.5 angstrom, then it can be written, or then it can be written as nu by rho is around 180 centimeter cube by gram. For lambda is 1.48 unusual behavior source. And then so this is the plot between that nu by rho and your lambda. Okay, so this is your AB and CD, this is your unusual pattern. Okay, and then at lambda is around 1.48 or unusual pattern, unusual behavior is there. So lambda around 1.48 exactly matches the K cell excitation energy of your number atom of the nickel atom. Then the energy of your X-ray around 1.4 at 1.48 angstrom is getting transferred as your kinetic energy of the ejected electrons. Okay, so now the role of the nickel filter. So for, if your target is copper, then nickel filter is utilized. If your target is cobalt, then iron filter is utilized. If your target is chromium, then vanadium filter is utilized. And if your target is iron, then manganese filter is utilized. So depending upon the type of target, your filter may also change. Okay, so this is how the role of the filter is determined. It reduces the intensity of the K beta to minimalistic level. Okay, but still in the background it comes, I will show in the last slide. So X-ray are the electromagnetic waves with a dual nature, and for the crystals with a long range periodic arrangement of the atom. If crystals are made up of the long range periodic arrangement of atoms, and of X-rays are electromagnetic waves with wavelength in angstrom region, then crystals will act as a 3D diffraction grating for the X-rays. Okay, so this is your like, these are your crystals. So crystal with a long range periodic arrangement of crystal is generally defined as a long range periodic arrangement of atoms. Okay, so if your crystal are made up of long range periodic arrangement of atoms, and X-rays are electronic wavelengths with a wavelength lambda, then these crystals will act as a 3D diffraction grating for the X-rays. Okay, so now if we define the Bragg's law, which is very important now. So we all know that n lambda is 2d sine theta. So if the wave is defined in a plane wavefront, parallel wavefront, then these two wavefronts are coming 1 and 2, and then the second one has to travel this additional path difference ml plus ln, and then this additional path difference can be defined as your 2d sine theta, that this one ml plus ln. So ml can be given as your d sine theta, and ln can also be like d sine theta. So this path difference is 2d sine theta. Okay, and then d is your HKL. This is difference between distance between your like uh, these are atoms. Okay, so n lambda is 2d sine theta, and from here we can write it in terms of lambda as 2d HKL by n sine theta. So now if we see more deeper in your Bragg's law, so Bragg's law considered crystals to be made up of parallel planes of atoms. So, okay, so these are the parallel planes of your atoms. And then the incident beams are reflected. These your incident beams are reflected specularly from these parallel planes of atoms in the crystal, with each plane reflecting only a very small fraction of the radiation. Okay, so and then these E, F, and DE are the can be written in terms of D is a planar distance between. Then it can be written as 2D sine theta. So n lambda will be 2D sine theta. So the constructive interference of the radiation from successive planes occurs when the path difference is an integral number of wavelength. This is the Bragg's law. Okay. So then further, if the path difference between these two the the same order, then your constructive interference happens, and then a higher intensity radiation will be seen. However, the others can, like destructive interference, can also be seen. And then this Bragg's law applies to all sets of crystal planes. The lattice can be deduced from the diffraction pattern, making use of general expression for the spacing of the parallels in the Miller indexes. So for cubic structure, D is given by 8 divided by root h square plus k square plus l square. So for different crystal structures, the formulas are different. We all read in previous classes. So this is the simple XRD pattern like what we see from the output. In the further classes, we will be discussing about the pattern, whether it is BCC, FCC, or some other kind, or mixture of all these. So and how to identify materials also. So this is what happens, like this is your strong intensity of prominent crystal peak planes. Okay, so these are your like higher the intensity, like stronger your intensity, then it says that your prominent crystal plane is that. Okay, and these are with a lower intensity. So these are your subordinate crystal planes, like they are present, but the prominent crystal plane is this. This is what from the XRD peaks intensity we can find out. And then this is the background radiation. It can be subtracted during analysis. So from after analyzing these, we get that your D spacing, like for around 2.88 D spacing, we are getting the intensity maximum around 100, and for 2.18 around 46, and so on. Okay, so and one more thing that here, like what I discussed, that generally the K alpha 1 is higher, like, right? So it is like the more probable that your K cell vacancy will be filled by your L cell, right? But it is nearer here. K cell vacancy will be filled by your L cell electron. Okay, uh, then the M cell, because then it has to travel more, right? So therefore the K alpha line is stronger than your K beta line. Okay, and yeah, more or less, yeah. So if anyone has any doubt till now, we can discuss. Okay.